Let's talk in more detail about the tools we use as astronomers. Here's an outline of the topics to be covered in this lecture. First, we're going to review some of the basics of telescope and light that we talked about last time. Then we're going to move on to the topic of telescope resolution, the Earth's atmosphere and space observations, and amateur astronomy. First, a review of telescopes. Telescopes can be described as having a certain capacity to gather light, or light gathering power. The larger the telescope, the more light can be gathered. Another aspect of the telescope is its ability to resolve things. In other words, how sharp can the image be made? This is called resolving power. And finally, we can talk about the ability of the telescope to magnify things and make them appear larger. As we talked about last time, the amount of light you can gather depends on the surface area of the mirror or lens. The larger the mirror or lens, the more light gets in. The resolving power of a telescope has to do with the ability to create a sharp image. And magnification power has to do with how big an image appears. As you might know, blowing up an image that isn't clear doesn't make it any clearer. So magnification is independent of the resolving power of the telescope. The resolving power of the telescope has to do with how clear the image is. The magnification merely makes it appear bigger, with whatever inherent resolving issues may or may not be present. As we discussed last time, there are a few types of telescopes. Refracting telescopes were the first kind of telescopes invented, and they use lenses to bend the light. Refracting telescopes bend the light to a focus, and then we use a secondary lens to look through it, or we place a camera at the focal point, or a CCD. There are certain disadvantages to refracting telescopes, which we discussed last time. Specifically, chromatic aberration is a big problem. Different colors of light bend differently than others. So the point at which blue light is focused is not the same point at which red light is focused. As you see in this cartoon, red light is focused at one point, while green light is focused somewhere else, and blue light somewhere else besides that. Here's another cartoon indicating the different places where different colors of light come to a focus in a refracting telescope. Other disadvantages we discussed last time had to do with the size, which could not be made very large, and they are also very expensive to make a large lens. Because lenses are made of glass, they tend to warp over time, just as you might have seen in an old building with real glass windows. So there are many disadvantages to a refracting telescope. Here is a huge 140-foot telescope which was built in 1673. Another type of telescope is the reflecting telescope, which instead of using lenses to bend light, uses mirrors to bounce the light and reflect it to a focus. Here's a diagram of how the light bounces off a mirror in a reflecting telescope. Most of the modern telescopes in use today are reflecting telescopes. They do not suffer from chromatic aberration problems. In other words, all the light wavelengths will reflect at the same point and come to a focus at the same point. They can also be made very large because we do not need to support a large piece of glass in such a telescope. And as such, they are often cheaper to make. This is what the first reflecting telescope looked like. Newton designed a secondary mirror to bounce the light off to the side for viewing purposes. A variation on this is the Schmidt-Cassegrain model, where the secondary mirror is bounced back through the primary mirror. This does not interfere with the image because light is so distant that you cannot really focus on the secondary mirror and the distant star at the same time. Last time we also talked about the Doppler effect, which had to do with light which was in motion. And just as with sound, the frequency increases when an object is moving towards the observer or the observer moving towards the object, and the frequency decreases when they are departing from each other. You can think of the object moving towards you as squishing the wavelengths to become shorter and closer together. This is a blue shift because blue light has shorter wavelengths, higher frequency. You can think of the object moving away from you as stretching the light wave out, resulting in longer wavelengths farther apart between each crest. This is called a redshift because red light has a longer wavelength and a lower frequency. On this diagram, we have wavelength on the x-axis and the strength of the light with this wavelength on the y-axis. So for a star which isn't moving, it appears maybe perhaps like this. Maybe this is its spectrum. But a star which is moving away from us will have the same features in the spectrum, only the spectrum will appear shifted towards the red end of the spectrum. On the other hand, a star moving towards us will exhibit the same features in its spectrum, the same dips and troughs, except that it will be shifted towards the blue end of the spectrum. This is how we know that stars are moving. A problem that faces astronomers is where we can put our telescopes. With our modern cities, there's a lot of light to compete with in gathering light from distant stars. This is a picture of Europe at night. You can see all of the lights from all the various towns and cities all across Europe. Here's a similar image of North America, and you can see in our general vicinity that there is plenty of light. Light coming from the ground, that is, not from distant stars. Contrast what it looks like on this map, or satellite image I should say, from our region to, say, Alaska, or the Hudson Bay region, or even west in Utah. Those regions that are more remote tend to have less light pollution. So one strategy is to place telescopes high on mountaintops. This avoids atmospheric interference, and if they are in remote locations, it avoids light pollution as well. Better yet, if we can place a telescope in outer space, then we are beyond the light pollution and all of the atmospheric disturbances. Why is atmosphere such a problem? Because the atmosphere does not remain still. The turbulence in the atmosphere causes the image to dance around. We call this phenomenon seeing. The more humidity and disturbances in the air, the worse the seeing. Let's review telescope resolution in more detail. When light enters the telescope, it results in a diffraction pattern, which blurs the image. We mentioned earlier that the larger the aperture, i.e. the larger the lens or mirror, the better resolution you can get. But another interesting fact is that the equation which dictates how small of an angle we can resolve also has the wavelength of light in it. Notice in this equation, alpha represents the smallest angle of separation that we can resolve, lambda represents the wavelength of light we are observing, and d represents the diameter of the aperture. Lambda appears in the numerator, meaning that the larger the wavelength of light, the longer the wavelength of light, the larger the angle is that we can possibly resolve. In other words, we cannot resolve things that are very close together if our wavelength of light is too long. We can make up for this by making the aperture larger. This is why radio telescopes need to have such a large aperture. Here I am with two of my daughters standing beside a radio telescope in Green Bank, West Virginia. You see the size of the dish is immense. This is because radio wavelengths of light have very long wavelengths, and therefore the telescope aperture needs to be made large in order to try to make up for this and get better resolution. Another trick to get better resolution is interferometry. This is a way of connecting separate telescopes together electronically to get a better resolution. Here's an example of interferometry at work. On the left you see a very blurry, spherical-like image that appears at first to be one star. But if we can get a better resolution by connecting and adding the signals together of more than one telescope, then we might get the image on the right, which shows us, with its better resolution, that there are actually two stars present, not one, since it's not blurred out and smeared out in a large sphere any longer. So how does the Earth's atmosphere get in our way, and what can we do about it? The Earth's atmosphere has certain windows in it. These windows are the kind of light that is allowed through the Earth's atmosphere. At other wavelengths, light is very effectively absorbed, and very little light of that wavelength reaches the ground. For example, you see that X-ray and UV light is almost opaque, and it would be very difficult to observe astronomical objects in these wavelengths if we had to look through the atmosphere. On the other hand, radio and visible present windows which we can put telescopes on the ground for and observe that way. But for other wavelengths, space is the answer. We need to get above the absorbent atmosphere and into space. X-ray telescopes, infrared telescopes, gamma-ray telescopes have all been put into space to observe different things. As we mentioned earlier, light pollution is another problem with ground-based astronomy. It's difficult in the blare of light pollution to see the distant objects that we're trying to look at. The light from those objects has to compete with the ambient light from cities and street lamps. The other problem with ground-based astronomy is seeing effects. Not only does the atmosphere absorb certain wavelengths of light, but it is not still. Wind, humidity, and other factors cause a blurring or smearing out or dancing of the star or other object we are observing. This instability is what we call seeing. Clever scientists have come up with ways to change for the turbulence in the atmosphere in real time. This is called adaptive optics. Mirrors are bent and adjusted in real time to compensate for the motion and turbulence in the atmosphere. But space is really the best solution. We have none of the problems of absorption, seeing, or light pollution when we have a telescope in space. This is why space-based telescopes are so popular. Here are some examples for you. Hubble Space Telescope is one of the most famous, but there are others. There are ultraviolet, X-ray, and infrared telescopes in outer space. Here are some images that Hubble was able to take. And you might be wondering how you can get involved in astronomy. Amateur astronomy is a fun hobby and can even take place with your naked eye or even just a pair of binoculars. Because our eyes need to adapt to darkness, it's a good idea, if you're observing in an amateur capacity, to stand in darkness for about 20 minutes to get your pupils to dilate to the size needed to detect dim objects. There are many telescopes that exist for amateur astronomers. You can buy a small 4 to 6 inch aperture telescope and be able to see lots of interesting things, such as our moon, the rings of Saturn, and the moons of Jupiter.